Hello, today we're going to be talking about the 12 basic functions, their graphs, their properties, and their equations for them. Let's jump right into it. So first off, we have the identity function, which is just a straight line that either goes up or down. Its most basic form, and the most common form that you'll see it represented, is y equals mx plus b, where this m term right here denotes the slope of the line, and this b term denotes the y-intercept, or the point in which the graph intercepts with the y-axis. Here you can see the parent function of the identity function, which is y is equal to x, in which the graph has a simple slope of 1 and it has a y-intercept of 0, 0. Now for the domain and range of the identity function, it is very simple. Since the graph extends infinitely to the left and infinity to the right, we can say that the domain of this would be x includes negative infinity and infinity, since it extends infinity to the left, negative infinity, and infinitely to the right, positive infinity. And for the range is much all the same. The range is y includes negative infinity to infinity, since the graph extends infinitely downwards and infinitely upwards, no matter the slope or no matter the y-intercept. So this is true for all lines, or just lines of the first degree, the identity function, that will have a domain and range extending to all real numbers. You can also denote that as all real numbers with this symbol right here. Up next, we have the quadratic function. You can see that the quadratic function is a parabola with a vertex and two distinct ends that point in the same direction. Now, one way that you can express the quadratic function would be by using the standard form, y is equal to ax squared plus bx plus c, but that is not the only way. Other common ways of expressing the quadratic function include the factored form, which would be y is equal to x minus a and x minus b, in which a and b in the scenario are the two intercepts of the parabola, where the parabola meets the x-axis, or the roots, or the zeros. All of those are the same thing, just different names for the same thing. Another common form you'll see a quadratic function in is the vertex form. A parentheses x minus h squared plus k, where h is the x-coordinate of the vertex and k is the y-coordinate of the vertex, and a in this scenario and also in the standard form represents how wide or thin the quadratic function is. Now you can see that for the quadratic function, it doesn't extend infinitely down and upwards. There is a limit as to how low it can go, or if you were to flip it around, there would be a limit as to how high it could go. So you see in this little drawing, it only goes as high up to a certain point. Now, this introduces some nuances in the range, but for the domain of a quadratic function is the same thing you'll see for the identity function. X includes negative infinity to infinity. That means x can be anything from negative infinity to infinity, since it is a continuous function. But for the range, it is nuanced. There will be either a lower bound or an upper bound up to where the range is. We'll use this red parabola as an example. Oh, I forgot to mention that this red parabola is the parent function. Y is equal to x squared. That's the parent function. You can see the range for that particular equation would be y includes 0 and infinity. Including 0, kind of excluding infinity, because infinity is not a defined number. It's just a concept per se. But yeah, you have the parent function for this. You have the domain and range. Oh, I also forgot to mention another important thing to notice about parabola is not only the vertex, but the fact that the vertex lies on a line, which is called the axis of symmetry, meaning that on this axis, the parabola will be mirrored, or it will look the same on both sides, which you can kind of see. It's very symmetrical. Now, you can't say the same thing for the cubic function. The cubic function, as we can see here, is not super symmetrical. In fact, the only way we can get the cubic function to look like itself would be rotating it along a point 180 degrees, which would be something that we would discuss in a later video. But introducing the cubic function, it is a function in which the x term is the highest degree is to the third power. We can see the standard form of a cubic equation as y is equal to ax cubed plus bx squared plus cx plus d. And there's other ways that it could be expressed. Most notably the factored form, which is much the same as the quadratic form. The parent function for this particular equation would be y is equal to x cubed, which is what you can see here. And something important to notice about the cubic function is that point that I mentioned earlier, that point which you would have to rotate part of the cubic function 180 degrees upon is known as the point of inflection, where the cubic function turns into concave up over here and concave down, which you can see over here. This is the concave down area. Now, for all our purposes, this is not super important. This is more pertinent to some calculus applications, but it is somewhat interesting to know. As for the domain and range of the cubic function, since it extends infinitely down and upwards, no matter the variables that you choose to plug in for A, B, C, and D, it is very simple and it is actually very alike to the identity function. You can see over here. So the domain of the cubic function bx includes all real numbers from negative infinity to infinity, and the range is much the same because it is continuous and it has no holes in the graph. The range would be y includes all real numbers from negative infinity to infinity. Yeah, very simple. Very cool graph. Now we get to the rational function. This is where it gets a little bit more complicated. So far, we've been talking about polynomials, in which it is just a standard line with x raised to a certain power. But this is not the case. Here we have the most basic rational function, and a rational function can get much more complex. You can raise x to certain powers, or you can include polynomials in the rational function. It's a lot. But here we have a very basic rational function, and this is in fact the parent function for the rational function. Y is equal to 1 over x. And we can see that it has two very interesting things, or maybe three. The first thing is it's not continuous. You can see here there are holes in the range and holes in the domain in which it's not continuous. But these holes are actually asymptotes, meaning that the graph will infinitely try to get as close to that number as possible, but it will never reach that number. So in this instance, the domain has an asymptote at y is equal to 0. No, sorry, pardon me. The domain has an asymptote as x is equal to 0, meaning that no matter what, the function will not be able to compute if x is equal to 0. And you can kind of see why here. If we were to plug in x equal to 0 over here on this side, you would get 1 divided by 0. And because of math rules, you can't divide by 0, and thus that's just not a number. And the similar thing for the range. Um, no number, you would not be able to get any number. 0 is equal to 1 over x multiplied by x. You get 0, x is equal to 1. No value, you can't get any value for x. You get that. So that's why y is equal to 0 is also an asymptote on this rational function. Now, because we're dealing with these asymptotes, there are going to be some holes in our domain and range. So you see for the domain of this function in particular, x includes all real numbers from negative infinity to 0, not including 0, and 0 to infinity. A little bit cramped over there, but you can still see that it's just everything but 0 in particular. Or you can do, another way to notate this really easily is all real numbers, x is not equal to 0. Now for the range, it is fairly similar. You can have range y includes all real numbers from negative infinity to 0, not including 0, and then 0 to infinity, then again not including 0. Or you can go the same approach as the domain, since it has the same asymptote with the same value. Range includes all real numbers except for y is equal to 0. Y not equal to 0. Up next, we got our first inverse. The square root function is actually the inverse to the quadratic function, meaning that if we were to take a basic quadratic function, say the parent function y is equal to x squared, we were to switch around the x and the y, x is equal to y squared, and then we try to isolate y by itself, so we just square root both sides. Square root x is equal to y. That would be our function. But an important thing to notice about the square root function is when we are taking the square root on both sides, you must remember to include the plus or minus. But because of the definition of a function in which we have one input has one output, we have to choose whether or not we want the positive square root or the negative square root of the answer. So in most cases, people tend to choose the positive square root to determine the square root function. And in fact, here you can see in red, we took the positive square root as our parent function. Root x is equal to y. That is our parent function. Now, if you wanted to adjust that, you can just make that negative. Over here, you have some variables that are very similar to the quadratic, in which you can just change how tall or narrow the square root function is with the a value, the location of the point with the b value, or how tall it is with the c value. Not tall it is, the location of the point along the y-axis with the c value. Now, with the square root function, you can see that if we ignore this pink part right here, that the function does not extend infinitely in any of the directions. It has a hard stop, in this case, at y at the point 0, 0. So we got to account for that when we're looking at the domain and range of this function. The domain for the square root function would be x includes, and this is just going for the basic parent function of the square root function. X includes everything from 0, because it includes 0 to infinity. Pretty simple. And the range is fairly similar. Range includes everything from 0 to infinity. And because we're taking the positive square root, that would be that. If it were, say, to be the negative square root, it would actually be y includes negative infinity to 0, like that. Just if we wanted to actually use the pink graph instead of the red graph. But since we're taking the red graph, that's not really pertinent. Up next, we got the absolute value function. Now, this is kind of a funky function because it looks like it should be a line or like a cross between a line and a quadratic, but it really isn't. Here you can see one of the standard forms for the absolute value. Y is equal to A absolute value bar x minus b absolute value bar plus c. A is just telling you how narrow or wide the absolute value function would be, and by adjusting the b and c variables you would be adjusting the point of the vertex over here and where it would be placed. So for example, if you plugged in say 8 for b and 4 for c, new vertex, the coordinate for the vertex would be 8, 4. Pretty self-explanatory. It looks something like a little bit taller, something like that, going off infinitely. Now, for the domain and range of the absolute value function, it is very similar to the quadratic function, in which you have a lower bound or upper bound because of this vertex. Anytime you have a vertex, you're most likely going to have some type of lower or upper bound. And so in this scenario, the domain is actually for the parent function of y is equal to absolute value x, you're going to have the same domain and range of x is equal to includes 0 and infinity, and for the range y includes 0 to infinity as well. An important thing to notice, or at least mention about absolute value, is what exactly defines absolute value. Absolute value is technically the distance that a number is from 0. So if you were to take a value like negative 14, it is 14 in units away from 0. So the absolute value of negative 14 would be 14. And that's why with the parent function, at least with no translations, it never crosses into the negatives, because every x value that you can place in, even if it's like negative 4 over here, it'll have a positive y value since it is a positive distance away from 0. If that makes any sense. Now we get into more complicated stuff, but this is actually very important to know. And one of the more common functions that you'll see, typically in banking, mathematics, and sometimes statistics as well, you'll see the exponential function. This is just one of the forms, one of the more common forms you'll see it in, of y is equal to a parentheses b to the x power, but you will also see it in its parent functions, something like y is equal to e to the x, where e is Euler's number for the constant of growth, and it is actually a very interesting story as to how we found it, but that's something for later. Now, something to notice about the exponential function is that it also, like the rational function, has an asymptote, but this time only an asymptote along the x-axis. That is because even if your x values are really, really small, the y values will never actually reach a certain number. In this case, the asymptote is at y is equal to 0, because no matter how big a number you plug into x, or how small a number you plug into x, any number to any power will always be 0. Always be greater than 0. So, accounting for that in the domain and range, we can see that the domain, it is still a continuous function, and it extends infinitely to the left and infinitely to the right. So it is a very simple domain. X includes infinity, negative infinity to infinity, or you can just do all real numbers, like that. Now with the range, it's slightly different, because we can see that it has a lower bound with that asymptote that is parallel to the x-axis. and it has some limitations. In this case, with the parent function, y is equal to the e to the x, we have the limitation of y includes all numbers greater than 0, not including 0, to infinity. Because the asymptote is at 0, the graph will never actually have the value of 0. Oh, another thing to quickly mention is that this a value over here is the initial starting value for the equation at y is equal to 0, or x is equal to 0, and this b term over here is the constant of growth. Because in this scenario, if you have x is equal to 0, the anything to the 0th power is just 1, so it'd be 1 times a, and that's why it'll be your usually initial value, or y-intercept in this case, for the exponential function. Up next, we have another reciprocal, this time the logarithmic function. The logarithmic function is actually not reciprocal, the inverse of the exponential function, where you have two very common forms of the natural log function and the base 10 log function. The only difference between the natural log and the base 10 function is the number that they choose to use as the base. For the natural log function, the base is actually e, Euler's number, whereas the base 10 log, it's kind of in the name, the base is 10. For these, because it is in inverses, because they're inverses, instead of having an asymptote that is parallel to the x-axis, they actually have an asymptote that is parallel to the y-axis. And in this particular scenario, they both share an asymptote at x is equal to 0. And for these parent functions as well, they'll both have a x-intercept at 1, 0. What's important to know about logarithmic functions is that these are the first, I believe, no, not the first, but one of the second function that we've encountered that has a domain restriction, because these functions do not extend infinitely to the left or right. In this particular scenario, the logarithmic function is bound to the left, where it actually cannot go any further left than x is equal to 0. We represent that in our domain by saying x includes all numbers greater than 0 up to infinity, not including 0, of course, because it can never touch 0. And for the range, we can see that it extends infinitely upwards and infinitely downwards for both the natural log and the base 10 log. So for the range, we can say y includes everything from negative infinity to infinity, or just all real numbers. Now here is where we get into one of our first trigonometric function, and this is the sine function. The sine function is a repeating function that oscillates between, at least the parent function oscillates between a peak of 1 and a trough of -1. It is continuous, going all the way to the left, infinitely to the left and infinitely to the right, but it is bounded because it never gets any greater than 1 or any less than -1. So this is another function that we can see that has range restrictions, because it never gets greater than 1 or less than -1, at least in its parent function. So we can see over here that the domain is very easy and includes all real numbers from negative infinity to infinity, but the range is different. For this particular parent function of the sine function, y includes everything including -1 to 1. Now if we wanted to manipulate the sine function by increasing its amplitude, we would add a coefficient up front. So 4 sine x would increase its amplitude from being 1 to being 4. That means that going from the base up to here, the sine is 4 units tall instead of being 1 unit tall. And the new range would be something like range includes all numbers from -4 to 4, like that. Next is something very similar, the cosine function. The only difference about the cosine function is that it is symmetrical about, at least the parent function, is symmetrical about the y-axis, meaning this axis of symmetry is over here. Whereas, I should have mentioned this with the sine function, the sine function is kind of an odd function, meaning that you would have a point in which you could rotate the sine function 180 degrees upon itself to get it to be mirrored onto itself. In this case, this point would be 0, 0, much like the cubic function. But with the cosine function, it is just symmetrical about the y-axis, which makes it really easy to remember, or really easy to distinguish between the sine function and the cosine function. Much like the sine function, the cosine function extends infinitely to the left, and infinitely to the right, but it is bounded by the peaks and troughs of the function. Once again, being 1 and -1 in terms of range. So expressing the domain of the cosine function, you get the domain includes everything from -infinity to infinity, but the range is limited, much like the cosine function. In this scenario, with the parent function of y is equal to cosine x, -1 to 1. Now, reaching the home stretch here, we have the greatest integer function, kind of a uncommon function you don't really see, mainly used in computer science, but in mathematics it doesn't have too many applications. I realized I made an error with drawing the graph, but it's okay. The greatest integer function is where you have any x value. Let's say, in this case, 0.4, and you would just take the greatest integer that is closest to it. So in this case, if you round up 0.4, you would get a y value of 1. And this is where you can kind of see the mistake in me drawing the graph. If I were to plot 0.4 as x, the y value should be 1 up here, so it would look something like that. Everything's shifted just a bit to make it accurate, but for all intents and purposes, it's okay. Something important to note about the greatest integer function, and it makes the first use of, at least of what we've seen, of closed dots and open dots, representing if a point is actually on a graph or it's not. The closed dot indicates that that specific point is yes on the graph, whereas an open dot means that no, this point is not on the graph, but it ends specifically at this point. Meaning that if you were to plug in a value of 1, it wouldn't be in this area, it would actually be up here in this graph, but we need some way to represent or distinguish where it stops and where it starts. And you can kind of see that this function is kind of wonky, having actually a continuous domain, but a limited range. Because this function goes infinitely on the negative side and infinitely on the positive side, infinity to the left, infinity to the right, and because every open dot is accounted for by another vertical closed dot, the domain is actually continuous, meaning that the domain includes all real numbers, just like all just the same as the identity function. X includes everything from negative infinity to infinity. The only problem is where you get to the range. And this is where we need to bring in another special symbol. With the R with a line running through it representing all real numbers. Just every number that you can possibly think of on the number line is a real number. We have another symbol for all integers, since you can't have any half values or quarter values using this greatest integer function. We would say the range includes all integers with a z with like a kind of hole in it. That's how I would usually draw it. Not a great drawing, but you can see how it's supposed to be represented. Another way that you could represent that would be saying that y includes the set 0, 1, 2, off to infinity. Just includes every single integer. But it is much more useful just to know the symbol of the integer symbol of all integers for the greatest integer function. Now, on our last function, this is a function that you will not see too often in algebra nor pre-calculus, but I think there are some applications in statistics and more higher levels of calculus. The logistic function. It is a kind of more intimidating function to look at, which is y is equal to 1 over 1 plus e to the negative x. And it's another example of a bounded equation where there is an upper bound and a lower bound, meaning that the range will never be bigger than 1 in this scenario or lower than negative 1. We can see with these asymptotes that the range will increasingly try to approach the value of y is equal to 1, but it will never actually hit it. And the same thing down here with the asymptote of y is equal to negative 1, parallel to the x-axis. The logistic function is also kind of an odd function, meaning that if you choose a point, in this case 0, 0 again with the parent function, that you can rotate part of the graph on 0, 0 to make it graph back onto itself if you were to rotate it kind of 180 degrees like that. You can kind of see it with my little drawing over here. With the logistic function, it has a very simple domain like before, like most of the functions that we've gone over today. X includes all real numbers, negative infinity to infinity, whereas the domain the range has a little bit of a restriction because it can't get any lower than negative 1. It can't get negative 1 or lower, or it can't get 1 or higher. So we would denote that as y includes everything from negative 1, not including negative 1 because negative 1's an asymptote, meaning it never actually gets to that value, to 1. Everything in between those two values, not including them. And that's it. That's all for the 12 basic functions. As a review, we have the identity function, the quadratic function, the cubic function, the reciprocal function, absolute value, square root, exponential, natural log, cosine, sine, greatest integer, and the logistic function. I hope y'all had a great day, and we'll see you next time.